This is Dr. Carroll. Today's video is about spanning trees. So this is in the context of graphs. So all trees are graphs, but not all graphs are trees. So what is a spanning tree then? Well, what a spanning tree is it's a connected, undirected graph without cycles. So the spanning tree if you start with a connected undirected graph G, then the spanning tree is a subgraph with all of the vertices and just enough of the edges to form a tree and no more. Okay? And what if we have a connected undirected graph with cycles though? Well, then what we need to do is we need to remove the edges until there's no cycles and you have a spanning tree. Well, that brings us to the question of how do you know if a graph has cycles? A connected undirected graph with n vertices must have at least n minus 1 edges. Okay, and a connected undirected graph with n vertices must have at least n minus 1 edges. Let's play around with this a little bit. So here we have one vertice and no edges, okay? And it's a connected graph and there's no cycles, right? Okay. Now if we add another vertex, is this connected? No, so we need to add an edge here. So we have 2 vertices and 2 minus 1 edges. Is there a cycle? No, there's not a cycle. Okay? So now let's add another vertex. Is there a cycle? Well, is it connected? No, it's not connected. We need to add in a vertex. So we add in a vertex and add in an edge. Is there any cycles? No. There's 3 vertices and 2 edges. Now if we add an edge, that will create a cycle. If we add that edge, it will create a cycle. Notice that? Now we have 3 edges and we have 3 vertices. Now we have a cycle. Okay? A connected undirected graph that has n vertices and exactly n minus 1 edges then cannot contain a cycle. Okay? And there's a more formal proof, but by induction, hopefully you saw that with that simple example. If you draw n vertices, you can connect them with n minus 1 edges, and if you add one more, then there's a cycle. But if you have just n minus 1, then there cannot be a cycle. Okay, so that brings us to the definition: a connected undirected graph that has n vertices and more than n minus 1 edges then must contain at least one cycle. Okay? So to remove cycles, then we remove edges along the cycles until we have n minus 1 edges. And then we know that we don't have any cycles anymore. Let's look at a depth first search spanning tree to figure out how we could calculate this. So what we're going to do is we're going to run depth first search. Make sure you've watched the graph traversals video. And what we get is a spanning tree. Let's look at the code. So depth first search tree, we're going to start with the vertex, not surprisingly. We're going to mark that vertex as queued and consider it visited, added to the tree. And then for each unvisited vertex U adjacent to V, then we're going to mark the edge from U to V. Now this is the only addition to depth first search. Okay, it's the only addition, and then we call depth first search tree on that new vertex. And there we have it. Okay, so let's see an example. So here we have this directed graph. And so we said if we do a depth first search and then mark the edges, then we can get a spanning tree. So then we would add A into our spanning tree. We would add B into our spanning tree. We would add C into our spanning tree. We would then add E into our spanning tree, D into our spanning tree. And then we need to come back up, come back up, come back up. and then F into our spanning tree. And that would yield a spanning tree that looked like this. Is this a tree? Yep, except I left the directed edges in. Oops. But if you just ignore those little arrows, it's a tree. Okay? It's a tree, and there's no cycles. Okay? And these images are available online. Okay, so that was depth first search. What about breadth first search? Same thing, and we're going to get a spanning tree, same as depth first search. We just need to add mark the edge from U to V again, and we'll get a spanning tree as well. And often multiple spanning trees are possible, as we'll see in a second. So let's go back to our original graph here. Now we're going to do a breadth first search and mark the edges, and then we're going to get a spanning tree is what I'm saying. Okay, so we'll add A to our spanning tree, then we're going to add B to our spanning tree, then we're going to add C to our spanning tree. And we're marking these edges as part of the spanning tree. Then we're going to mark F as in the spanning tree, and we're going to add this edge here. Now we're going to do all vertices that are depth of 2 away from our starting vertice. So then we're going to add D into there, coming from B, and then we're going to add E in there as well, and we're going to mark this edge and this edge, and you can just pretend with me that they are undirected edges. Okay, and here we go. And is that a tree? Well, yes, especially if you took away the arrows. But that's a tree, and there's no cycles, and there we go. Okay, now let's imagine that we're going to form a new company, and we're going to lay down fiber optic cable, and we're doing it in the mountains of Peru. And so we've got this great financial opportunity, but what we're trying to do is we're trying to figure out the least cost to go from one city to another so that all the cities are connected, and we want the least cost. How are we going to do that? Well, in comes minimum spanning tree to save the day. And a minimum spanning tree is a spanning tree, but it has the minimum total cost of all the edges. And so it has to be a weighted graph. So a common algorithm to solve that is Prim's algorithm. What we're going to do is start with any vertex and add the lowest weighted edge that adds a new vertex, okay? And so we only want a new vertex. And here's some high-level code to do that. Prim's multiple spanning tree. We're going to start at a vertex, and we're going to mark that vertex as visited, and we're going to add it to our minimum spanning tree. And while there's still unvisited connected vertices, what we're going to do is we're going to find the least cost edge out of all of the edges that are are connected to a vertex in the multiple spanning tree and connected to a vertex that is not. Okay, so we're looking for the least cost edge that gets us to a new vertice. And then we're going to mark that one as visited, and then we're going to add that edge into our minimum spanning tree. Okay, let's look at an example. So now we need to have some weights on here. So this same graph, but with weights. Okay, so you could imagine there could be a mountain here, and so the cost to lay fiber optic cable here is very high, where this could be a valley, and this could be a valley, and this could be existing conduit or something along those lines. So what we want to do is we'll start at A again, and we're going to add in the least cost edge that gets us to a new vertice. Well, that's clearly 1. Okay, so now A and B are in our minimum spanning tree, and so is this edge. Now we evaluate all edges to see which one is the least cost edge. Well, we have an edge here, 5, 10, 8, 7, and 2 are our options. Well, we're going to go with 2, of course. So now F is in the minimum spanning tree, and so is this edge. Now we reevaluate all possible edges. That gets us to a new vertex. So we have 5, 10, 8, 7, and 9 and 11. Well, 7 is the lowest, so we're going to add this edge and this vertex into our minimum spanning tree. Again, we're going to reevaluate all of the edges and get the lowest cost one. That's going to be 4. And then we're going to evaluate all the edges. It gets us to a new vertex, and now we're only lacking E, so then we consider 6 and 11, and we settle with 6. And that yields a tree, a minimum spanning tree like this. This edge is here, this edge is here, this edge is here, this edge, with those vertices. So if we had an internet connection here, and we're trying to get a fiber optic cable to all of these cities, this one would be the least amount of cost to connect all of the cities, okay? And that's found by summing them up. And so there is no spanning tree that has a cost lower than 20. There may be others that have 20, but none, there are no spanning trees that have a cost lower, total cost lower than 20. And that's it for the video today.